Alright everyone, welcome back. Today we're going to be talking about optimization problems. Now this is probably the section that gives Calculus 1 students the most difficulty. And believe it or not, it's not the calculus that gives the students difficulty, it is the algebra and relating variables to one another that actually causes difficulties. Now, one of the most important applications or uh, of calculus applications of calculus, as I just mentioned, involves determining minimum and absolute values. Minimum and maximum, not absolute, maximum values. Now, um, sometimes you may hear when you're talking about business, like the maximum profit that a company may achieve, or the least amount of money that you need in order to be profitable, and all of these ideas that have to do with finding the minimum value of something or the maximum value that a quantity can achieve can be modeled by the use of calculus. This is why um, a lot of economic students opt to take calculus 1, and also business students. Now, to find maximum and minimum values of a problem, you have to follow some guidelines. And I'm going to do first a motivational example, then I'll give you the guidelines, and then we'll do an example or two more. Um, and that hopefully will be enough for you to understand the main ideas of this section. So first of all, let's start with an example. So we have a manufacturer who wants to design an open box having a square base and a surface area um, of 108 square inches. Now, the question is, what dimensions for the box will produce a box with maximum volume? Okay, so then we have an open box, so an open box will look like a cube, but with the top removed. So think about this ugly drawing that I just made as a cube, but the top of the cube is not there. So we have this side is there, this side is there, this side is there, this side is there, but the top is missing. Now, when we're dealing with a basic cube, the volume of a cube is the length times the width times the height. Now, we just said that the base is a square. So this is very important because a square, you remember what a square is. A square has area that's given by length times width, right? So it's given by the length times the width, or height. You know. So if this is the base right here, then we're saying that, and a square, by the way, all the sides are the same. So this side is the same as this side. So what we're saying is that this long side here has length x, and this side here has length x as well. Now, the height of the box is the one thing that we do not know what it could be. So the height of the box could be something that's not actually the same as x. It's not the same as the base, so we'll call it h for height. And how do we know this is the case? Well, if you ever receive a package from Amazon, for example, sometimes you may receive boxes that are not very tall, but they have the same width in their bases. So like you could place one over the other, and let's say this is a different box now, but it's a longer box. It's like a terrible drawing. Yeah, it's a pretty terrible drawing. This corner is supposed to be there. In any case, maybe I'll show you a picture of boxes after this example. In any case, so this being the regular volume formula, if I replace length times width times height by the variables that I'm using here, I have length is x, width is x, and the height is h. Well, x times x, we know that is x squared, so we get x squared times h. So we have related the sides of the box with respect to volume. Now this equation that we have up here, this is called the primary equation. So this equation is called the primary equation because it gives a formula for the quantity being optimized, because we're trying to find the max or min of this. Now, how do you find the surface area of this particular box? Well, remember the surface area we could get by basically finding the area of each side of the box and adding it up together, right? That's how we find surface area. Now, this particular box does not have a top, so we have to keep that in mind. It's open. Let me put it back down here. So it doesn't have a top, but this side is x, this side is x, and the height is h. We know that the base of the box has area x squared because it's length times width, and if you just put it flat on the table, the sides are the same, so you just multiply them and you get x squared. Now, this piece here, this piece in the front here, this piece in the back, and the piece on the side, on this side, they each have the same area, because to get them you just take the side x, and they all share at least that side x, which means that this top is the same as well, this top pieces, and they all share the same height. So each one has area x times h. And to find the surface area now, we simply add up the areas of each of the sides. So how many sides do I have? You have 1, which is the back side, 2, which is the front side, and then the left side. So that's 4 sides. So in reality, I have 4 of these, and then the base, which is just 1 of these. So to get the surface area, of the box, we do the following. We do S for surface area is equal to, like I just said, the area of the base plus the area of the 4 sides. which means that S is actually equal to x squared, because that's the area of the base, plus 4 times the number of sides that I have. I have 4 sides, so it's 4 times x times h. If you don't see it, what I did was I just combined this. The formula is actually S equals x squared plus xh plus xh plus xh plus h xh 4 times, so it's the same thing as 4 times xh. Okay, so now we have a formula representing surface area. And why do we need the formula for the surface area? Well, because the manufacturer wants a surface area to be of 108 square inches. So if we want to optimize the volumes, we want to find the maximum volume for this problem. We want to find the maximum volume. So if we actually want to solve this, we need to solve this equation. But we have no information about h in this equation, or x for that matter, but you know, it's easier for us to solve and for h in this problem. So since we want to maximize volume, and the volume formula we have is in terms of 2 unknowns, namely x and h, we will use the secondary equation. This is the secondary equation. To help us isolate a variable. So what do I mean by that? We know something about surface area. The problem tells us that we want a surface area of 108 square inches. And we just figure out an equation that relates the open box to the surface area. So we have the surface area is given by x squared plus 4xh. So x squared plus 4xh. And we know that we want that to be equal to 108. So what can we do here? Well, we could either solve for x or we could solve for h. Now, solving for h is much simpler than solving for x. Hopefully you can see why that is the case. So if we were to solve for h, what do we do? Well, we move x squared to the right side, and we're left with 4xh equals to 108 minus x squared. Then we divide both sides by 4x, and we have that h is equal to 108 minus x squared divided by 4x. But now we have a value for x. No, for h. Now we have a value for h. And because we have a value for h, we can plug it in into our original equation. Because remember, our original equation that we had, our primary equation, was x squared h. This had 2 unknowns. But now we can substitute for h. And notice that h is written in terms of only x's. So if I substitute back h in here, for what we just found it out it's equal to, then the whole equation of volume is now in terms of just one variable, and we can actually solve this. We can actually solve this with the skills that we have learned so far, because it's a function of one variable, and we've been dealing with them since the 8th grade. Okay, so if we multiply through, we got 108 x squared minus x to the 4 divided by 4x. And then you could simplify this a little bit. 108 is definitely divisible by 4. I believe 27, yeah, 27 goes into it. And then you could cancel one of the x's there. So actually do it slowly, so equals here. So this is 108 x squared divided by 4x minus 4x to the 4 divided by 4x. So volume is equal to 27x. It's 27 times 4 minus x cubed. Ooh, I added a 4 here. There's no 4 up here. So minus x cubed over 4. No, something look weird. Yeah, okay. So now we have a formula for the volume. Notice that this formula is in terms of just x's. And now we can start to find out what value is going to maximize or minimize the maximum volume. But before we do that, we want to talk about the domain. So let's talk about the domain of x. Remember, the domain is all of the values that make sense for the problem. So clearly, because we're talking about volume and we cannot have negative volume, x has to be bigger than or equal to 0. We cannot have negative volume. So that's number 1. We definitely need to have it be bigger than or equal to 0. Now, we know that the area of the base is x squared. Okay, we got that all the way up here, up there. And not only do we know that the area of the base is x squared, but we know that we want the surface area to be 100 square inches. So if the surface area is at most 108 square inches, this is the worst case scenario. The worst case scenario, like if you have an open box, let me just do it one more time. So what's the worst case scenario? The worst case scenario is that the base, which we know something about, which is x squared, is that the base itself is 108 square feet. And if the base by itself is 108 square feet, then we don't have really a box. We have just the bottom of it, because then there's no height for any other sides. So that's the worst case scenario. So that means that in this scenario, the area of the base is equal to 108. But we know that the area is also equal to x squared. So if we take the square root on both sides, we get plus or minus radical 108. Now, the reason why we're doing it with the base and not the sides is because we don't know anything about h. So remember, the height is h. So you could have said, well, what if we just focus on one of the sides? Then we have to worry about what h is, and we have no idea what that is. But we do know how to relate the area with just one variable. So this becomes actually an easier problem. So now we have a constraint. So this is called a constraint on the axis. So this has to be less than or equal to the square root of 108. Just to put it into perspective, let's say somebody told you, you have a cup. Hopefully this example works. You have a cup, and the cup has, you could put in 16 ounces of liquid in it, right? And then you're given 2 bags with some liquid on it. So you have bag A and bag B. You want to make sure that you fill this cup of 16 ounces. Well, one of the ways that you could do it is to just put 100% of A and none of B. So that's what happened up here. We put everything into just the base and nothing on the sides. Or you could put everything from B but not from A, or you could go 50-50, or you could go 25-75, and so on. So we took care of the worst case scenario, which was what if the base has all of the square footing. Okay, so this is the first thing that we do. We find out what our domain is, and this is going to help us when we end up looking for the max and min, because it's going to make our work a little bit easier, because it will allow us to eliminate solutions that are not part of the solution set. So we will have solutions for the equation that we use for the derivative that will not be part of our solution set because they're not part of the domain of our solution. Okay, so now that we have found our interval, we're looking for x values on the interval 0 to square root of 108. So if the solution is not on this interval that we get now, then we disregard them. Now, much like we did in the previous section, where we found the max and minimum, to find the maximum or minimum, we have to find the critical numbers. So we need to find critical numbers by using the derivative. So let's do that. Our volume formula that we just solved is 27x minus x cubed over 4. So 27x minus x cubed over 4. If we take the derivative v prime of this, we get 27 minus 3x squared over 4. That's what the derivative will be. Now remember, to find critical values, we set the derivative equal to 0. So we have to find out when is this equation now equal to 0. So that's what we're interested in solving. Well, let's move the 27 to the right side. So we're going to do minus 27 on both sides. And now instead of dividing by 4, let's multiply both sides by 4. Get negative 3x squared. And again, 4 times negative 27 is going to be negative 108. Then let's divide both sides by negative 3. We have x squared is equal to, okay, so 3 goes into 10 3 times, so that's 18, and 3 goes into 6 into 18 6 times, so that's 36. Minus and minus cancels, so you have x squared equals 36, and now you take the plus or minus square root on both sides, and you get that x is equal to plus or minus or equal to 36, which means x is equal to plus or minus 6. Now, the critical numbers are plus or minus 6, but negative 6 is outside of our domain. Remember, our domain is 0 to radical 108. So we do not consider it. Negative 6. Now, we have that V, the volume, is a maximum when x is equal to 6. So V is maximized when x is equal to 6. Now, let's go back to the problem here. If x is equal to 6, then what is the maximum volume that we get? If x is equal to 6, we have volume divided by 6 is going to be 27 times 6 minus 3 times 6 cubed over 4. Yeah. So if you solve this equation right here, you're going to get what the maximum volume is. And once you have the maximum volume, then you could actually get the dimensions of the box. And you could even get it before that, because it has to add up to, the sides have to add up to 108 when you multiply it. So in fact, it's even easier than that for this problem. Yeah. Let's go back to our box problem. So we had x squared, x squared minus 4xh equals to 108. This is from our surface area equation. If you plug in 6 into this and solve, then you'll get the solution for h. So you got 6 squared minus 4 times 6 times h equals to 108. It's actually much easier than doing this one. So you get 36 minus 24h equals to 108. You have minus 36 on both sides. So you have minus 24h. Is this right? Oh. Let me see. Oh, it's a plus, not a minus. Yeah, plus. Yeah. There's a plus in the formula. So plus 24h, and then this is going to be, I believe this is, 72? And then you divide by 4, by 24, you're going to get 3. So h is equal to 3. So that means that the sides of the box that work are 6 times 6 times 3. Because x is equal to 6 and we have two of them. We have x squared times h. That's the volume. So that equates to 6 times 6 times 3. So this is how you go about solving this optimization problems. Now, there are actually an infinite ways of how to approach the problem. This is the best way to do it, though. You could try to estimate the problem a bunch of ways. Let me give you some guidelines about on how you actually should approach all these problems, and then we'll do another example. So this is some guidelines for solving. Applied min max problems. Right, so number one, you want to identify all given quantities and all the quantities to be determined. Which is what we did. We identified the sides, we identified the equation that we needed to work for, and we identified that we were looking for the volume. Number two, we want to write a primary equation. For the quantity that we want to maximize or minimize, or I would just simply say optimize for the quantity we want to optimize. Number three, we want to reduce the primary equation into an equation involving a single independent variable. Number four, we want to determine the feasible domain. problem. And number 5, finally, want to determine the desired max and min values by using the calculus techniques. Techniques previously covered, such as the first and second derivative test. Okay, let's do another example. Let's see what we can cook up. So, let's see, what do we have? Okay, so we have, let's do this one. We have a rectangular page. It's a popular one. That is to contain 24 inches of print. The margins at the top and the bottom of the page are to be 1.5 inches, and the margins on the left and right are to be 1 inch. Now the question is, what should the dimension of the page be so that the least amount of paper is used? So what should the dimensions of the page be so that the least amount of paper is used? This is a very useful problem for those of you who are going to be majoring in English and you want to save the earth by using less paper and you have a lot of essays to write. This problem is actually very useful for that. In any case, I like to draw things to make sense of them. Here we have a piece of paper. Typically, pieces of paper are rectangular, right? Now, we are told that there is a margin at the top and the bottom of the page. So when you have a margin, that's just an area where we typically don't write. So we have a margin at the top and bottom of the page, and we're told that that margin is 1.5 inches on both sides. So this is the part where you really have to pay attention and have some knowledge. So we have a margin 1.5 inches at the top and the bottom. Okay. Now we also have margins to the left and to the right of the page. And this margins, so this margin that I wrote here is for this. And then this margin that I'm writing on this side, and let me put it in red actually. So this margins from here to here are 1 inch each. So we know from the previous problem that if we want to find the area of a rectangle, it's the length times the width. So the area of a rectangle is length times width. Some people say also length times height. Now, we have to be a little more careful here because we are talking about two pieces of information. So we are told the following piece of information that is very important. The rectangular page is to contain 24 inches of print. That 24 inches of print is what's going to be on this inside. So we really have two two rectangles working here, an inner one and an outer one. Now for the outer one, what we have is we could call, let's say, this side x, and let's call this side y on the inside, not the outside. This piece right here, y. So we will get the dimensions of what these sides are and then what the outside is. So for this piece and this piece, we have x and we have y. And then for the entire page, what we have is x plus 1.5 plus 1.5, because we have two of them. So if we were to contain the entire distance of this side, it will be this times y, but y, if we were to do the whole page, will be this side, 1 plus 1 as well. Well, this simplifies to x plus 3, because 1/2 plus 1 plus 1, 1.5 plus 1.5 basically is 3, and 1 plus 1 is 2. Okay, so we're trying to look again for the dimensions such that this inner piece gets maximized. We know that this inner piece has lengths y and x, and then we know that we have margins to the left, to the right, and the top and bottom. Now, the area of the inside, I just said, is x times y. Okay, so the area of the inside is x times y, which is basically the same thing as this, length times width, right? But now we also know something about that area of the inside. That area of the inside, we want it to contain 25 inches of print. Okay, so we want that area to be equal to 24 inches of print. So it simply means that x times y is equal to 24. Now, notice we have our primary equation, which is this. This relates the entire problem. And then we have a secondary equation for the inner piece. Both of them are in terms of x and y. I am going to solve for one of the variables so that I could plug into the other equation and hopefully have an equation of just one variable. So what I'm going to do is, and it doesn't really matter if I solve for x or y first, but I am going to solve for y because we typically always solve for y. So if you solve for y, you simply divide both sides by x. If you're solving for x, you divide both sides by y. The solution will be the same whichever way you do it. And at least for this particular problem, it doesn't become easier one way or the other. So we have y is equal to 24 over x. Now that we have a solution for one of the variables, we can use that solution in our principal equation. So we have a is equal to x plus 3 times y plus 2. But now we know that y is equal to 24 over x. So we have x plus 3 times 24 over x plus 2. And now this becomes our new equation in one variable. Notice that there's only one unknown, and that is x. We could FOIL this out. If we FOIL, we get 24, because x times 24 over x is just 24, plus 2x, plus 72 over x, plus 6. So we get 6 plus 24, that's 30, plus 2x, plus 72 over x. So this is now our new equation. Notice that we went from an equation in two variables to an equation in one variable. Okay, now before we take a derivative, so this was, if we go step by step, this was step number 3. So we found all the quantities given. We found a primary equation. That's step 2. Step 3 is to solve so that we only have one equation. Now step 4 is to find a feasible domain. Again, because we're dealing with area, and area is always positive, x has to be bigger than or equal to 0. Has to, because the area is always positive. Now, in fact, this is all that we care about for this particular problem, that x is positive. X technically here could be as big as we want, because we just care about the inner area here to be 24. So the outside could be as big as we want it to be or need it to be. So x definitely has to be positive. So now we can actually start taking derivatives. So let's take the derivative. The derivative of this, of 30 plus 2x plus 72x, is the same as the derivative of this with we bring back up the negative exponent. And now we take the derivative and we get 2, the derivative of 30 is 0, the derivative of 2x is 2, minus 72x to the minus 2, which is the same thing as 2 minus 72 over x squared. Now, we took the derivative. This is step 5. This is the last step. Take the derivative, find the critical values, and then make a determination. So to find the critical numbers, we set the derivative equal to 0. When is the derivative equal to 0? The derivative is equal to 0 when 2 minus 72 over x squared is equal to 0. If we move 2 to the right side, if we subtract 2 on both sides, we get negative 72 over x squared is equal to negative 2. And then here we could actually cross multiply. So if you cross multiply, we get negative 72 equals to negative 2x squared. And we could divide both sides by negative 2. And we have x squared is equal to 36. And then we take the plus or minus square root, and we get the answer is plus or minus 6. And again, much like the other problem, in fact, it's a coincidence that we get 6 again. Much like the other problem, we do not need to consider negative 6 because we said that our domain was x being positive. So we don't consider negative values. So much like example 1, we do not consider x equals negative 6 since it is not part of our domain. All right. Well, now that we have found a value for x, what can we do? Well, we can actually plug into one of the equations that we have. Now, you could plug into this equation, but that will actually be much more complicated. Notice that here you have an equation in one variable. Instead of plugging into this that has a y in there, let's actually plug in here for x, and we get the value for y. So if you plug in here, so that's y equals 24 over x. If you plug in 6 for this, we have 24 over 6, which is 4. So now we have a value for y and we have a value for x. So we have that x is equal to 6, y is equal to 4. So we found the dimensions. We found the values for x and y. Now we could find the dimensions for the page. The dimension of the page, again, were given by x plus 3 and y plus 2. That's the original function that we had. To find the dimensions, we take the length times the width. So remember, this was an equation for the length of the whole page. This was for the width of the whole page. What we found was the length and width for the inner piece, for this inner piece right here. But if we actually, for the printable area. Now the dimensions for the, let me just call it length. For the whole page, it will be 6 plus 3, which is 9. Let's say this is the width, or the height, I think. I have that completely backwards. 4 plus 2, which is 6. So we have a 9 by 6 piece of paper. And that is honestly how all of these maximization and minimization problems go. The most important thing and the most difficult thing of all of these problems is actually correlating the correlating the variables with an equation. That is something that you will need to get good at. Now, again, something that you should remember are the formulas. So if if you remember the formulas that relate area and other variables, then you should be fine. You should definitely be fine. Wanted to have time. Maybe I'll do one more example. It's a short one. Okay, so let's say we're given the following. We're given that x plus y is equal to 20, and we want to find the greatest product. So we want to find the greatest product of x and y when their sum is 20. So now, you could do this with a table because it's not that long of a problem. So let's say if you did a table for x and y, you're looking for values that add up to 20 but multiply to a big value. You could begin with 0 times 20. Well, 0 plus 20 is 20, but the multiplication of that is 0, right? And you could do it for every single value, and you will see that eventually you will get it. But this is not feasible when the problems are very large, because when the problems are very large, then it's going to take you forever to do this. And as you'll begin to see right now, if you do this like I'm doing it, this is definitely going to take you forever. So you could do it this way, or you could use some calculus. So first of all, we can quickly identify our domain. So I'm going to do that first. Our domain, clearly, x has to be bigger than or equal to 0, because we're talking about positive numbers. I should have said that up there. Find the greatest product of x and y when their sum is 20, and let's say x and y are both positive. Because you could multiply to negative numbers and get a positive number, so you could do that. Or you could have something like a number bigger than 20, like you have x, let's say, be 32 and y be negative 12, and of course that's going to be bigger than a number that's strictly between 0 and 20. So we want this number to definitely be between 0 and 20. Okay, so that we have found our domain. Now I want to find the maximum or minimum value for this. Now we know, because I gave it to us, that x plus y here is equal to 20. Now we know that we're looking for the product of x times y. So this is what we're given, and what we're looking for is for the maximum product of x times y. We're looking for the maximum of this. This that we were given to start, this we call a constraint. And this is what we're looking for. Looking to maximize. Okay, so I have two variables, my two equations, my primary equation and my secondary equation. This is also my primary equation because it's the one that maximizes the product. Just remember, I'm looking for the greatest product. So if I'm given a problem like this on an exam, let's say, what will I do? Well, I will work with this to isolate a variable so I could substitute in here. It doesn't matter which one you choose, but I'm going to choose to solve for y. So I'm going to mean that I'm going to have y equals to 20 minus x. Simply move x to the other side. Now that we've done that, we can substitute y up here. So in x times y, we could substitute for y. So we get x times 20 minus x. And if you FOIL, you get 20x minus x squared. And now we have found our primary equation. We have found our domain. We have written the equation into just terms of one variable. So we went from having two unknowns to just one unknown. So now we can take the derivative. So we have p prime is equal to 20 minus 2x. And then now we could find when this is equal to 0. It's a very easy one. Minus 2x is equal to minus 20. So that means x is equal to 10. Okay, so when x is equal to 10, we have a maximum. But now if x is equal to 10 and they both have to add up to 20, then you could guess what the value for y has to be. It also has to be 10. You could actually solve for that right up here because y equals 20 minus x is 10, so y has to be equal to 20. So when x is 10 and y is 10, we have our maximum value, which is our maximum product, which is 100. So the value that has the greatest possible product between x and y, such that they both add up to 20, is when x is 10 and y is 10, and we get 100 as the maximum. I am available for office hours. The notes that I posted on Blackboard do a very good job explaining these optimization problems. I highly suggest that you also go over them because there are many more examples that you should see, especially involving circles, which I didn't do in this section, or triangles or cones. So I definitely suggest that you review those as well on the notes. As far as the final exam for this class, there is a problem on optimization, and typically it involves either volume or volume triangles or rectangles, but it's not more difficult than the first example that we did right now. You're typically given enough information to do the problem very quickly. That is it for this section. Thank you for your time.